Well, thank you. Thank you.
Protect your eyeballs.
We could just take a tour around the lab if you want to.
Okay.
So all this runs on 3,000 psi of oil versus the air that we have back here. It doesn't really look like it's moving, but it's compressing. That shock is hydraulically locked out, and we're pushing on it with thousands of pounds of force. We're just trying to find an initial failure point on it. This here is an eyelet fatigue test. So you can't really see this one either, but we're actually wiggling that eyelet, trying to put a torsional load onto it. A coil shock, no coil. That's an example of an accelerated valve durability test. We'll crank up the compression on the shock, overfill it with oil, and then just slam it through its travel. So this is our new 32 XC fork, brand new chassis. This is running a torsional test, so we're twisting the whole chassis. This new chassis is way stiffer than last year's fork. I can't give you exact numbers, but if you go over to the screen here, you can kind of get a ballpark, right? So here's our old chassis, the red one, and here's our new chassis. The steeper the slope, the stiffer your specimen is. I can't give you, we've removed the actual values from it, but you can see that it's actually quite a bit stiffer than our old XC4. That's a spring fatigue test going on over there. We have to get it moving because we don't want paint to crack it. So that's an example of we're exploring new springs at the moment. So we're moving that guy as much as possible to try to get the paint to crack on it. If you don't want paint to crack, then your spring rusts, then your spring breaks.
Can we go look at it?
Yeah. So it's just running a simple sine wave, but we're trying to get paint to crack on it, which then lets moisture in, which then that's when you get a spring breaking. And that slow stroke, we call that a characterization stroke. So it does that every once in a while, and we'll look at those data points to see if the spring is lost. Some of our tests will have these buckets, and you'll see like a drain on it. And we actually spray calibrated dirt onto it, because every sample you need to spray the same dirt, right? You can't have like mud on one and sand on the other. So we actually buy dirt. You know, the first thing anybody does when they get on their mountain bike is they jump on their fork and they say, this fork feels sticky. This is a friction study. So it goes through various fast, slow, all sorts of different cycles. This air piston is pushing backwards on the fork because your fork obviously isn't straight up and down, so you always have a little bit of a side load on it. So we'll induce a side load and then we'll move it through its travel. Right now it's actually moving. It's just moving really slow because that's when you feel stiction, is when you're just barely moving. We're really proud of our forks now. They feel awesome. We experiment with different oils, different foam rings, different seals. We just, every combo you could think of, we pretty much run it. And we have some profile tests going on over here that are pretty. So here, this is a simple fatigue test. So it's meant to fatigue the disc brake mounts on the fork. That's the whole test. It does that 100,000 times. So this one's what we call a profile test. So you can see it's moving in just arbitrary stroke length. So what we did is we took one of our design engineers here, strain gauged his bike up, and had him go ride one of our local trails, which is go hammer on the fork, right? So that's his bike ride that he's doing right now. So some portions, like right there, that was the flat part of the trail. He wasn't really hitting that much, and a minute from now you'll see the fork just going crazy, right? So this is cool because instead of us having a guy ride for a year, we can just loop this for days, and obviously the machine never gets tired. So this speeds up testing quite a bit. So it goes through all this erratic test motions, and then you'll see it stop. And it goes through a stroke just really slow. And when it's doing that, we take 1,000 data points per second. So you can see the degradation of the damper that happened through all this crazy movement in between those characterization strokes. I mean, you can kind of see the trail, right? So that's the actual signal coming out of the fork. This is similar. It's a profile test, but for a shock. So this is one of our guys riding, I believe, out at demo, which I think you guys are going to ride maybe this afternoon or tomorrow, one of the days.
Tomorrow.
But this shock is riding that trail. This runs for 3 days. If we didn't have a fan on this shock would just, it would be hot. In 3 days, we could pretty much get the life of the shock. This is interesting. So with carbon stuff, obviously, you know, people want it to be strong, but you want it to be compliant too. You don't want a bar that's just vibrating you to death. for the wheels. You want them to be radially stiff. That doesn't really matter that much because you have a tire and you've got a suspension fork, right? So the radial stiffness of a wheel is, you want it to be stiff, right? But with the front wheel, with these Aero wheels, our goal was to increase torsional compliance or lateral compliance. So this test is measuring lateral compliance. So you can see we've got two different actuators here. So this actuator is loading up your wheel as if a rider is sitting on it. And then you'll see this actuator is pushing down. So it does push down on it. So this actuator is pushing down. And then this encoder here is figuring out the degrees of roll of the actual rim. So when it pushes down, we're seeing how much your wheel actually deflects. In the past, carbon stuff has been, it can kind of beat you up. It's too stiff. So the goal has been trying to build in compliance. This is a simple disc brake flange fatigue test. So you can see that this is acting like your rotor here. So we're simulating a 200mm rotor, and we're essentially trying to shear the 6-volt flange off the hub.
Does it eventually come off?
So we run this 100,000 times, and we put 1,500 foot-pounds of torque on the flange, and most of the time it makes the 100,000 cycles, which you would never do. I mean, I would never do that. That's like just 100,000 times. Just can we do a dead immediate stop? I don't know. You can't even do that, right? Because you'll start skidding on the ground. And we've got another lab. We built everything in that room. These we bought off the shelf. This station's wiggling a fork. You don't want to see any evidence of this test over here. So these are like state-of-the-art dynos. You don't hear any crosstalk, so anything hypersensitive goes on in this room. This is all gravity-driven stuff. So we're pulling away drop sticks, hitting a pedal, hitting a handlebar, hitting a wheel. Sometimes you just need to drop something heavy on something else. I mean, here we have one of the new Aero bars running a fatigue test. Our goal with the Aero bars was to have a higher impact strength but a more compliant bar, which sounds counterintuitive, but you can fully do it with carbon. And what's new for us this year is actually different SKUs of bars are going to have different carbon layups. So each bar really is different. Sometimes companies will make like an 820 bar, and their 800 bar, all they do is they chop off 20mm. Same handlebar, right? So like with these Aero bars, we're actually, every layup is different. So we're trying to get that ride feel out of like whatever width or height or rise you have. This is for forks, and the goal of this is to break the fork every single time. So we're not trying to see if something survives this test, we're trying to break it. And really the goal is your product needs to stay in one piece. I mean, it's purely safety. We don't want blowers flying off, we don't want steer tubes snapping. That's completely unacceptable. So if we snap a steer tube in there, it's immediate pump the brakes. I mean, that product's not going out to market. It looks rudimentary, but it's really critical just to completely break your product. This is held up by electromagnets. You press the magic button, this drops, catches your wheel, which would be down here, and completely destroys the fork. And usually what you get out of it is just a fork that looks like this. It's just, it's still a fork. It doesn't work, but it's just bent. When you turn it on, the alarm starts going off, the siren starts buzzing, you have to wear safety glasses, but a testament to our fork is it does stay in one piece, so you don't have debris flying all over the place. That's a damper shaft internally in a shock. We're really loading that piece of, this is an aluminum damper shaft. We're testing aluminum versus steel at the moment. So this is running, I don't know, probably 40, 50, 60,000 cycles, and we're just slowly just pulling on that thing. At some point it will snap. These two big noisy machines here, so we're driving this drum with a motor. The wheels passively coast over the drum, and there's actually big bumps bolted onto that drum. It's hard to see because it's going so fast. Another machine over here, I have no idea. This works real good for like initial like rim extrusions when they're trying to prove out a new piece of product. Nobody rides their bike straight and just runs over stuff all day long. So this is like a good benchmark, but it's not very realistic. So that's why we built this guy over here. So this one's actually driven by a chain. versus this one where the drum is spinning. And you can see we put a carriage inside of it, so it's actually tilting back and forth. It'll go through a sprint where it goes back and forth really quickly. It'll coast down to 0 and then speed back up. So we're trying to copy how you actually ride your bike. Really noisy, it takes up a lot of room. It's kind of slow, but we get real good results out of it. We're looking at it simple, what we call a duty cycle test. All we're doing is we're cycling it through 75% of its travel. I know you've seen when you pull an old fork apart and you've got the 2 bushing rub spots where you can see right through the ano, like down to the tube. So that's this guy. These are leak chambers, so we'll like cycle seat post cycle shocks, and then we'll put it in this tube here. It creates a complete vacuum, and we'll fill the shock or the post, whatever it may be, up with helium, and it creates this vacuum. And then this is called a sniffer, and if it sniffs any helium, it starts making all sorts of noise. Something you can never do by, you know, over pressurizing spring soap on it or something. We really want to create a vacuum chamber, and we use helium because the particles are real small. So if you have a really small crack, you'll be able to pull helium out. That's pretty much it for our test equipment.